This screen shows the graphical user interface of our 1.5G NOMA demonstrator. In the following, we detect 3 active users with 3 receive antennas. Each user sends BPSK symbols on the same time frequency resource. Initially, we detect the first user. Switching to detecting the second user. On the left side you see the error rate of MMSE, MMSE-SIG and our ML approach. On the right side you see the processing time of all 3 algorithms. You can see that the processing time for successive interference cancellation increases as we go down in the SIC chain. Switching to detect the third user. Processing time is increasing again, but the machine learning approach remains comparable to MMSE. Note that our machine learning approach can calculate the receive filter for each user independently. Therefore, it can be implemented in parallel for all active users. In the following, we change to a configuration where we have more active users than receive antennas. Now we detect user 1 of 6 with only 3 receive antennas. Switching to detecting the second user. We see a degradation in the performance of machine learning algorithm. This is an indicator that we need more training samples for the learning phase. Therefore, we enlarge the number of training samples from 50 to 650 samples. The expected performance will be achieved again, with a small but visible jump in machine learning processing time. Switching to detecting the third user. MMSE and MMSE-SIG show a worse error performance than machine learning. Switching to detecting the fourth user. Now the error performance for ML is also bad. ML filter is solved in a higher dimension of a reproducing kernel Hilbert space using a weighted sum of 2 kernels. We can adjust the weights between the linear and the nonlinear kernel to use a more nonlinear solution. Adjust linear and nonlinear weights to 50% and 50% respectively. ML outperforms the linear algorithm MMSE and the nonlinear algorithm MMSE-SIG. Switching to detecting the fifth user. Switching to detecting the sixth user. Adjust linear and nonlinear weights to 10% and 90% respectively. We can sum up that machine learning outperforms nonlinear algorithms like MMSE-SIG, and its complexity is similar to a linear algorithm such as MMSE. Each user sends pilots during training phase and data on the same time frequency resource, non-orthogonal signaling, which may also solve the pilot pollution problem. ML can also learn the receive filter independently for each user, and it is therefore suitable for parallel implementation.